Hello everyone, welcome to a series of lectures in linear algebra. We would like to begin our journey to linear algebra by studying something which you are all familiar with. You studied this lesson when you were in high school mathematics. This topic is about systems of linear equations. But for this lesson, we would like to begin with some definitions that will help us have a proper language in the study of linear systems. So in this lesson, capital F should denote the field of real numbers or the field of complex numbers. Kung ito'y gagamitin sa applied mathematics, for example, if it involves real numbers, we will only restrict ourselves to R. But if for some reason you would like to include the imaginary numbers, then we should set F to be C. In any case, we shall always assume that F is either R or C. The elements of F, once F has been selected, will be called scalars. If n now is a positive integer, we define the set Fn, so we read this symbol as Fn, not F raised to n. No, it's not an exponent. Fn is the set of all n tuples of elements a1, a2 to an, where each of the ai is an element of F. For example, if F is chosen to be R, then F3 or R3 consists of ordered triples a1, a2, a3, where each of these symbols are real numbers. This is sometimes what we call as a three-dimensional Euclidean space. In this case, the elements of the set Fn will be called vectors. Or if you want to emphasize the number of coordinates in a vector, we say that this is an n vector. Take note that in our case, vectors are ordered n tuples, meaning to say, the order of these elements matter. Meaning to say, if you somehow disarrange the position of these elements, then it doesn't mean the same thing anymore. In fact, two vectors will be equal if and only if they are equal position-wise or component-wise. These are called the components of the vector, these being the first, the second, and the nth component. So these two vectors will be equal if and only if a1 is equal to b1, a2 is equal to b2, and so on, an is equal to bn. These vectors can be added to form another vector. To add the vector a1, a2, an to the vector b1 with components b1, b2 up to bn, we simply add them component-wise. When we say component-wise, the first components are added to get the sum, or to get the first component of the sum. The second components are added to get the second components of the sum, and so on. Aside from addition, we can actually multiply a scalar to a vector. When we say a scalar, it's an element of F. So if R is a scalar and this is a vector, then we can multiply the scalar R to this vector by simply multiplying the scalar R to each of the components of the given vector. As an example, if we want to add the vectors in R3, 2, negative 1, 4, and negative 7, 3, 2, we do this component-wise, meaning to say 2 plus negative 7 is negative 5, then negative 1 plus 3 is 2, and then 4 plus 2 is 6. If we now want to multiply the scalar negative 2 to the vector 2, negative 1, and 4, then the result is another vector of the same dimension. So to do this, we simply multiply the scalar negative 2 to each of the components. Negative 2 times 2 gives us negative 4. Negative 2 times negative 1, it will give us 2. Negative 2 times 4 is negative 8. So the answer is as shown. Take note that if f is taken to be the set of real numbers, then f1 or r1 is just the real number line, or it's the set of real numbers. Geometrically, we represent the real number line by an infinite straight line. Selecting a point, call it 0. Selecting another point, we call it 1. Then the distance represents 1 unit. Thereby, from this, we can locate all the rest of the real numbers in this real number line. If n is 2, we get the set R2. The set R2 consists of all ordered pairs x, y, where x and y are real numbers. Geometrically, this set corresponds naturally to the set of all points in a plane, where an x-axis and a y-axis has been set. For example, in this Cartesian plane, this point is represented by the ordered pair 2, 1, or the vector 2, 1. Sometimes we would rather represent the vector by drawing an arrow from the origin heading towards the point 2, 1. If now n is 3, R3 is now the set of all ordered triples x, y, z, where x, y, and z are real numbers. This is represented by a three-dimensional space, as shown. In a three-dimensional coordinate system, we now have three number axes, which are the x-axis, the y-axis, and the z-axis. Imagine that this point is the one corner of, let's say, a room, right? Can you imagine that? So every point in this space may be assigned to an ordered triple of real numbers. Take note that if n, or the dimension of the space, is less than or equal to 3, we may use x, y, and z for convenience, or as we are used to using them. But if n is more than 3, we shall now use the subscript notation because we may run out of the English alphabet in that case. If f is C, or the set of complex numbers, by the way, for your information, the set C of complex numbers is the set of elements of the form a plus bi, where a and b are real numbers, and I is a non-real element whose square is negative 1. Two complex numbers may be added as shown. It's like a plus c. It's like combining similar terms, right? We can also multiply them. This multiplication comes out of the FOIL method, the so-called FOIL method. You multiply the first terms, the outer terms, the inner terms, and the last terms. Now take note that the last terms, bi times di, gives us bdi squared. Because I squared is negative 1, this is equal to bd. And this term corresponds to the term over here, right? If n is a positive integer, by Cn, we mean an ordered n-tuple of complex numbers. Each of these are complex numbers. For example, the ordered triple, negative 7 plus 2i, comma, negative 2i, comma, square root of 2 plus 3i, is an element of C3. Here, the first component is the complex number is negative 7 plus 2i, the second component is the complex number minus 2i, and the third component is the complex number square root of 2 plus 3i. At this point, we can now give a definition for a linear equation. So, a linear equation, usually in n unknowns, x1, x2, up to xn, is an equation of the form a1x1 plus a2x2 plus and so on, plus a and xn equals b, where each of these, a1, a2, an, and b, are all scalars. So the unknowns are the variables x1, x2, xn each represent a scalar, unknown scalar. Hence, because there are more than one unknown in this case, a solution could be represented by an n vector. So, formally, a solution to this equation is just an n vector of scalars. So now this is an n-dimensional vector or an n vector, so that if we substitute s1 to x1, s2 to x2, sn to xn, this makes the equation true. True meaning both sides of the equations gives us the same result. Take note that the set of all solutions of this equation, or the solution set of this equation, is a subset of Fn, because a solution is of the form of S1, S2 up to Sn. As an example, you can consider the linear equation in 4 variables: 4x1 plus 3x2 plus x3 plus 2x4 equals 5. Notice that the vector with components 1, negative 1, 0, 2 is a solution to this equation, because if one substitute 1 to x sub 1, negative 1 to x sub 2, 0 to x sub 3, 2 to x sub 4, we get an equation which is true. On the other hand, the vector 1, 1, 1, 1 is not a solution, because if you do the same substitution and you look at this equation, this is false. Why? Because the left hand side simplifies to 4 plus 3 plus 1 is 8 plus 2, 10, and 10 is not equal to 5. That's why this equation is false. Notice that if you look at this equation, you may solve x sub 3 by isolating it on the left hand side and putting these terms on the right hand side as shown. This means to say that the value of x sub 3 is dependent on the value of x sub 1, x sub 2, and x sub 4. Meaning to say, if one assigns a number to each of x sub 1, x sub 2, and x sub 4 arbitrarily, if you put something here, and something here, then you get a unique value for x sub 3. Hence, we may write the solution set as follows. If you set x sub 1 to r, if you replace this by r, and you replace this by s, and you replace this by t, then you can write the solution set of this equation as follows. You can write it as r being x sub 1, s being s sub 2, and x sub 3 being this one, 5 minus 4, r minus 3, s minus 2t, comma, t, because x sub 4 is set to be t. Notice that you can write the solution set this way. Sometimes this is what we call as the parametric form of the solution, because we use parameters to represent the solution set. So in this example, this equation has infinitely many solutions. You can select arbitrary values for r, s, and t and produce a solution. For example, if we set r to 1, s to 1, and t to 1, for example, then what do we get as x sub 1? X sub 1 is r, so that's 1. X sub 2 is s, so that's 1. X sub 3 is 5 minus 4 times 1 minus 3 times 1 minus 2 times 1. And that is 5 minus 4, that's 1, minus 3, negative 2 minus 2, that's negative 4. X sub 4 on the other hand is t, so that is 1. Therefore, 1, 1, negative 4, 1 is a solution. Right? You can check directly by making a direct substitution to this equation. See that the equation is false. So if true. Now, if you now select another set of values for r, s, and t, then you will produce another solution. So this solution set is represented by a 3-parameter parametric equation. Now there is a trivial case that we need to look at. This is when the coefficients of the unknowns are all 0. This is interesting because no matter what x sub 1, x sub 2, and x sub n are, the left-hand side will always remain to be 0. Thus, as a remark, if the right-hand side constant b is 0, then you can see that every vector in Fn is a solution. So if this is 0, then no matter what vector in Rn or Fn that you will pick, it will always be a solution. On the other hand, if the right-hand side is not 0, then this equation cannot be satisfied, therefore it has no solution. Having defined a linear equation, we can now define what we mean by an m by n linear system. So first, we select two positive integers, m and n. An m by n linear system is just a conjunction of m linear equations, each in n unknowns. Again, what do we mean by a conjunction? A conjunction is a compound statement or a proposition which is connected by the connector n or the connective end, no? So meaning to say, when we write equations this way, this is a composite or compound statements connected by end. Therefore, in order for this system to be true, each of these equations must be satisfied or must be true. We usually represent an m by n linear system in this way. Notice that in the coefficients of the unknowns, I am using two subscripts as a convenient notation. Why? Because now here, the first subscript represents the order, or in what equation is that a coefficient. For example, this is equation 1. Now if we call this equation 1, if we call this equation 2, you call this equation m, no? Then each of these coefficients, because the first coordinate is 1, meaning to say they belong to the first equation. The second subscript, on the other hand, represents the subscript of the unknown. As you can see here, for example, a21, meaning to say it is the coefficient of x sub 1 in the second equation because the first subscript is 2. Now take note that each of these aij and bi must be constant. Again, when we say m by n, m equations, linear equations, bawat isa ay may n na unknowns. So aij and bi are in F, I from 1 to m, ito yung I, ang j natin pa ganito, j from 1 to n. And of course, a solution to this linear system is just a vector, which is a solution to each one of these. As this is a conjunction, for that to be true, each of the component statements must be satisfied or must be true. We say that this system is consistent if it has at least one solution. Otherwise, if it doesn't have any solution, we say that the system is inconsistent. In the case where m and n equals 2, there is some kind of geometric interpretation to a 2 by 2 linear system as follows. Of course, f here has to be r to be represented this way. Now take note that in elementary algebra, an equation of this form may be represented geometrically by a straight line. So therefore, this is a pair of straight lines. For this to be satisfied, we need to find a point that satisfies these equations both at the same time. Hence, we are actually looking for the point of intersection. So when these two lines intersect, the point of intersection is the unique solution in this case. If this pair of lines does not intersect, just like in this case, then there is no solution. And it is possible that these two equations is represented by the same line. So in this case, the two lines actually coincide. In this case, there are infinitely many solutions. Of course, if in the case where m and n are 3, each linear equation in 3 unknowns geometrically is represented by a flat plane in a 3-dimensional space. So for example, the figure on the left, represents a 3 by 3 linear system wherein each equation is a plane, and these planes intersect at a unique point. Hence, in this case, the system has a unique solution. In the case of the second figure, although the planes intersect pairwise, when you say pairwise, kahit aling dalawa nag-i-intersect. For example, itong dalawa nag-i-intersect dito. Itong dalawa nag-i-intersect dito. Itong dalawa nag-i-intersect dito. But, remember, for a system to be solved, considered solved, a solution must solve everyone. So we are looking for the intersection of the three. Here, there is none. So this is an example of a linear system that has no solution, even though pairwise the equations have solutions. Now it is even possible, that for a 3 by 3 linear system to have infinitely many solutions. I don't have a picture for it, but let me try to draw it for you. For example, when they intersect this way, I don't know if I can give justice. I hope I can. Sorry. Paano ba? I think we can draw it this way. No? Yan. Can you imagine the picture? The planes intersect. It's like, when it's like the pages of a book, no? Ito yung pinaka-rim at dito naka-attach yung mga pages ng ano. So in this case, the intersection is an infinite straight line. Therefore, because there are infinitely many points in an infinite straight line, then this has infinitely many solutions. Tama ba? Alright. So let's continue. So two linear systems are considered equivalent if they have the same solution set. It is possible that two linear systems may actually look differently, no? But when you look at the solutions, they seem to have the same solution set. For example, these linear systems, systems of equations, 2 by 2. Pareho silang 2 by 2. Ito, mukha lang one unknown yan, but actually two unknowns din yan. Ang coefficient lang ng x ay 0. You can consider it that way. Kapag graph natin ito, if we try to solve this graphically, hindi naman natin business yung pag-graph dito because that's elementary mathematics. So I graph these lines for you. If you want to recall how to graph, you can pause this video and try to graph these lines on your own. And see that each of these pairs, nag-intersect sa point na 1, 2. Hence, ang solution set nila parehas yung singleton containing the point 1, 2. May unique solution, parehas yung linear system. Hence, they are equivalent, although they look differently. But you see, when you look at these equations, or systems rather, you see that although they are equivalent, the second one is easier to solve. Why? Because the second equation tells us directly what is the value of y by simply dividing 7 on both sides. In fact, y is 2. From there, we can work here on the first equation, substitute y equals 2, and then you can solve for x, which is 1. Unlike here, we have to do some, if you remember the algebra of this, you have to do some elimination or maybe a substitution, etc. So this way, this manner of solving, yung isa-solve mo muna yung y, and then substitute mo pataas para ma-solve sa x, we call this a back substitution. For example, although I may not be able to show it to you, but later we will show, these linear systems are actually equivalent. But my question is, which one is easier to solve? Actually, it is the second one. In fact, the second one is already practically solved, right? Because z is 1, z is 1. From the second equation, we can solve y. That's minus 2 plus z. So that's negative 2 plus 1, negative 1. And from the first equation, tawagin natin itong 1, 2, 3. From the first equation, x is negative 4 minus 2y plus 4z. Because we already know the values of y and z, we can just directly substitute. Tama ba? Kindly check if I make mistakes in my computations. So this is negative 4 plus 2, negative 2 plus 4, that's 2. So therefore, the system has a unique solution, and the solution set contains only the vector 2, negative 1, 1. Take note that we don't have 3 solutions. We only have 1. Ang bilang, ang isang solution kasi ay isang vector. Remember that. Okay? This is why our discussion will, this example will lead us to a problem of trying to, let's say you're given this system. Can I transform this system to an equivalent system which is easy to solve? Now, can we do that? Can we make some transformation? Yes, that's our direction. Now, we have the following theorem and observation by Gauss. I think this is some of these are quite obvious. Now, suppose that a linear system, tawagin natin may dalawa tayong linear system. Isa is represented by heart, the other linear system is represented by a diamond. Suppose that a linear system heart is obtained from a linear system diamond by performing any of the following operations. Let's say nag-swap ka ng dalawang equations, you swap two equations. Or let's say you multiplied a non-zero scalar to both sides of the equation. Okay? Or let's say ni-replace mo yung isang equation by its sum with a scalar multiple of another. Let's say, ito yung ginagawa natin paborito ng high school, no? What we do is we add one equation, we add one equation to a multiple of another. The sole purpose of number 3 is when we try to eliminate variables or unknowns, if you can remember that. Say multiply equation, we add equation 3 to 2 times equation 2. Parang ganon. Then, the resulting system, if this was obtained from here by doing any of the following operations, then you do not really change the solution set, because the resulting statement, kasi ang linear system is just a proposition, diba? Conjunction. For example, why can we swap two equations? Kasi in a conjunction, the order of the statements is immaterial. For example, you have P and Q, that's equivalent to Q and P, right? So if you multiply both sides of an equation by a non-zero scalar, well, that's multiplication property of equality. Okay? Bakit non-zero? Kasi kapag 0 ang pinang-multiply mo, so parang tinatanggalan mo na ng karapatan yung equation, magiging 0 equals 0, magiging ano na siya, true na siya. Kapag may true na kasi sa conjunction, you can drop it. Diba? Parang tinatanggalan mo siyang karapatang magdikta tungkol doon sa solution. I mean, yung condition niya, hindi mo na kino-consider. That's bad. So, we do not multiply by a zero scalar. We can only multiply both sides by a non-zero. Remember that. Okay, basically, number 3, para ka lang nag-a-add ng dalawang equation. Parang dalawang equals, pag in-add mo, lead to another equals. Right? For example, let's try to perform the operations according to Gauss, to solve this linear equation. Now, the goal is, if we will go back here, the goal is, pag meron kang ganito, you would like something like this. So here you can see, x here was eliminated as well as here. In this case, y here was eliminated. We would like to somehow make it in a triangular form. Later on, we will call this the echelon form. Okay, so let's say you wanted to solve this. So to do this, first we would like to swap equation 1 to equation 2. By the way, label natin to ng 1 at 2 ha. Equation 1, 2, and 3 by the way. So why do I want to swap E1 and E2? Kasi, tignan yung gagawin ko. Pag swinap ko yan, magiging ganito, right? Meron ka ng bagong 1, 2. I-update nyo rin yung number ng equations. Kasi kapag 1 yung nandito, I can easily eliminate this. For example, I can eliminate this one by multiplying a negative 2 here and then add. Right? That's kind of easy. Kaya gusto kong 1 yung ginagawang, ang tawag dito, pivot or pivot. It depends on what English you are using to. So, for example, if I want to eliminate a 3x, I can multiply this by negative 3. I just consider the additive inverse of this and multiply here and then add. Right? See, the next step. I can replace the second equation by E2. I mean this. Ito na ha. Ito ng E2. Ito 1. Ito ay 3. Right? Replace equation 2 by equation 2 plus negative 2 times E1. The purpose of that is to eliminate the 2x over here because we don't want any more x's here. Right? So that's it. Ito yung mangyayari dyan. If you want to do it on your own, you may pause this video and try to check my work if my calculations were correct. Okay, I will not do the manual computations anymore. I did it earlier. Then, ito na yung bagong equation 1. Take note, 1, 2, 3. I could replace equation 3. Ito yung eliminate ko ngayon, di ba? Replace equation 3 by equation 3 plus the sum of equation 3 plus negative 3 times equation 1 because I have an x here. May tanong. Sir, paano kapag wala akong x dito? Let's say, 4 ito. Huwag ka na makipag-swap. Diba ito 4? Huwag ka na makipag-swap. Ang gawin mo na lang para magkaroon ka ng x dito, you can now multiply both sides by 1/2. Therefore, magkakaroon ka na ng x dito. Pero, kaya lang ako nag-swap kasi may nakita ko x doon na available na. Kung walang x dyan, you can just use the second operation, multiplying a non-zero scalar to both sides to produce a 1. Multiply mo yung multiplicative inverse ng 2. In that case, okay? So, let's go back. So, replace equation 3 by equation 3 plus negative 3 times equation 1. Ito yung mangyayari. So, you see, the x's below are now eliminated. Luckily, we have produced a y here. Why? Ito yung gagawin naman nating pivot or pivot to delete the y's below it because we want a ladder, no? We want a ladder or an echelon. Right. Okay. So one more operation. We would like to eliminate minus 8y. How? By adding this to 8 times this equation. So ito na ngayon yung bago mong 1, 2, at 3, right? Yan. So, we replace the third equation by the sum of it with 8 times the second equation. Thereby giving us the following. Now, we would we don't like a 7 here, right? What do? We multiply 1 over 7, no? The both sides of equation 3, therefore producing this. In fact, alam na natin yung value ng z right away. Did you see that? Did you see that? Yes, no? So as you can see here, you can now directly solve it using back substitution. So here z is 1, y is negative 2 plus z. Substituting z, you get negative 1. Using the first equation, solve for x, that's negative 4 minus 2y plus 4z. Substitute the values, the known values of y and z. You get x equals 2. Therefore, xyz, the vector xyz is equal to the vector with components 2, negative 1, 1. Ibig sabihin nito, x is 2, y is negative 1, and z is 1. As you can see, when we try to solve linear systems, what really matters, no, are the coefficients of x, y, and z, or the unknowns, right? Do you observe that? Meaning to say, these variables are actually just placeholder and they don't really play a role important to the calculation. The solutions will really depend on the values of these coefficients in the constant over here. So we would like to allow ourselves to relax a little bit by trying to not mind these unknowns and through the use of matrices. Now, so let us now define an m by n matrix. An m by n matrix is just a rectangular array of scalars arranged in m rows and n columns, and it's usually expressed in this way. Again, you see that the representation uses two subscripts. The first subscript represent kung pang ilang row. Ito yung first row, second row, mth row. Yung second subscript represents kung pang ilang column. First column, second column, nth column. Now, the element A12, for example, is called as the 1, 2, and 3. Or these are called the entries of the matrix. More specifically, yung Aij is called the Ij entry of the matrix. The vector of entries with first subscripts I is called the ith row. For example, ito yung first row, second row, no? Pare-parehas yung first subscript. When you look at the vector of entries with the same column number, second, what do you call this? Second subscript, we call that the jth column. This is the first column, the second column, and the nth column. Okay, this is just a matter of definition. Now later on, yung mga rows, we will write it in this way, in this manner. Now, later on. But for now, wag muna. Tapos yung mga columns, itatayo talaga natin literally nakatayo kasi columns. But for now, we shall adopt the vector notation. Okay? For example, this matrix is a 3 by 4 matrix. Can you tell why it's a 3 by 4 matrix? It has 3 rows. It has 4 columns. Right? Okay? The second row is the vector -1, -pi, 4, 7 over 8. The third column is the vector square root of 3, 4, -98. The 2, 3, and 3 of this matrix is 4. Now, associated to each m by n linear system is its augmented matrix. Meaning to say, this is this is our representation of linear system using matrices. Instead of writing the linear system this way, we intend to write the system in this way by simply ignoring the unknowns, no? In a way, yung mga entries na to kasi ay may address. Kaya alam mo kung kaninong equation yan, tsaka kung kaninong unknown nakadikit. No, yung mga scalars natin sa kanan, yung mga right hand side ng equation, nilalagay natin sa last column. And then, naglalagay tayo dito ng imaginary line. Ang matrix, wala naman talagang line dyan. No? But, para makita natin kung ano yung right hand side, no, nilalagyan natin ng line dyan. We call this an augmented matrix, the augmented matrix of this linear system. Take note that if the system is m by n, the augmented matrix is m by n plus 1 because we're adding another column, one column, for the vector of constants na nandun sa right hand side. Alright? For example, this linear system, no, if we try to delete the unknowns, no, and let the matrices work for you, ganito siya. Ito yung augmented matrix ng linear system, diba? Mas madaling tignan ito kaysa dito. And in fact, because it's in matrix form, the computer can easily read this one. Aside from this one, more than this one. Ito kasi, Machine readable, ito hindi. Human readable. Parehas ng human readable, but for a machine, it prefers something like this over this one. Ito naman, the augmented matrix of the linear system is the following. Alright? Do you see that? Yeah. You see, kapag may mga nawawalang unknowns dito, it's not because they are gone, really. Actually, it means to say that there is a 0x over here, there's a 0x here, there's a 0y over here. Meron talagang 0 doon. That's why, in our augmented matrix, meron tayong 0. Again, we prefer this form over this form because this is easily solvable using back substitution. Therefore, in terms of matrices, we prefer a matrix like this over this one. This matrix, no, over here, ito yung sa susunod na definition, is said to be in row echelon form. A matrix A is said to be in row echelon form, or REF, no? If the following are satisfied. Ito yung mga rules para masabi natin naka-REF ang isang matrix. Number 1, rows of zeros. Kung meron mang row na puro 0 ang laman, dapat, if there's any, they should appear at the bottom part of the matrix. I think you know which one is the bottom part, no? Yung nasa baba. Para naman sa bawat non-zero row, for each non-zero row, the first non-zero entry from the left must be a 1. Ito yung pivot na tinatawag natin kanina. Alright? For each non-zero row, pag ang row may non-zero element, at ang kauna-unahang non-zero element from the left must be a 1. And this one is called the pivot or the pivot of the row. Now each pivot must be in a column to the right of the pivot in the previous row. Oh my gosh, what do you mean by this? So, imagine that this is your matrix. Let's say this is a pivot. Let's say that's a pivot and that's something else, no? Yung star experiment, it's something else. Now, let's say there is a row before it na may previous row. Siyempre, kung naka-row echelon form to, dapat kung non-zero row ito, ang unang entry mula sa kaliwa ay 1 ulit. Tapos ito, something else. Yeah. So, these are the pivots. You look at the pivots. Ito ay pivot, pivot. Alright. Now, let's look at this pivot. The pivot on the second, and the fourth column. The pivot on the fourth column must be to the right. Mali. Each pivot, for example, itong pivot na to, itong 1, is in a column, fourth column, to the right of the pivot in the previous row. When you look at the column numbers of the pivot, I mean, ito ay 2, nakita nyo? Ito ay column 2, ito ay column 4. Nasa kanan ng 2 yung 4. Kasi yung 1 na ito, mas mataas yung row number. Well, anyway, condition number 3 simply says that the pivots must be arranged in a ladder form, like this. No? Parang kung 1 ito, yung susunod na 1 nandito, yung susunod na 1 nandyan. Hindi kailangan equally spaced. Basta kailangan naka-ladder. Do you understand? No, meron tayong additional condition. A matrix is said to be in RREF. By the way, for a matrix to be in RREF, it must be first in REF. Kailangan satisfied muna itong 3 conditions. So parang para maging RREF ka, dapat REF ka muna. Tapos may additional condition. Kailangan every pivot is the only non-zero entry in its column. Why? Wag mo na yung why. How? Ibig sabihin, kung may pivot ka dito sa second row, dapat sa ibabaw nun at saka sa ilalim, puro zeros. Whenever you have a pivot in a column, all the rest in that column must be zeros. When you look at the matrix here, no, for example, ito ay nasa matrix in REF siya, row echelon form. Kita nyo naman, ang first non-zero entry from the left are all ones, and these ones are arranged in echelon form. No, yan ang sabi ng echelon form. But this one is not in REF. Why not? Why not? So for example, when you look at this pivot, ayan, no, yung column niya, it has a 2. Look at this 2. This is a problem there. No? We wanted to zero that out. Ano mangyayari kapag ganun? Kung gagawin mo 0 to, 0 ito. Ang linear system na ano niya, na corresponding niya, it's actually solved already. Yun yung x, y, at z. Kaya gusto natin sometimes RREF. In fact, in practical situations, we would prefer the RREF over the REF because it will reveal the solution faster, no? Almost hindi ka na magba-back solve dito kapag naka-RREF. You will see this in the future examples. And in fact, there's one more important reason why we prefer RREF over REF. Kasi ang isang matrix, laging may REF yan. Pero posibleng, for example, can you transform this matrix to an REF, a matrix in REF? Let's say I ask 2 students to do that. Now these two students can give me 2 different matrices in REF, no? And they are both correct. Pero kapag RREF ang hinanap ko, dapat pareha sila because RREF of a matrix is unique, while ang REF, a matrix in REF equivalent to a given matrix is not necessarily unique. That's why that is one important advantage of RREF over REF, yung uniqueness. You will see that later. For example, determine if each of the following is in REF. Of those which are in REF, identify which are in RREF. Okay. Tingnan natin. Condition number 1. At dito muna tayo sa first matrix. May 0 row ba? Do we have any 0 row? Yes. And it is in the bottom, so that's not a problem at all. Now we look at the non-zero rows. So these are the first, second, and third. Look at the first non-zero entry from the left. Non-zero entry. Huwag ignore mo lang yung 0. So as you can see, they are all ones, right? Now, are these pivots arranged in echelon form? Yes. This pivot in second column is to the right of a pivot, no, in the previous row. In other words, ganyan, no? Ayan, no? Ito yung echelon or yung hagdan. Echelon, may echelon. It's like, hindi siya physical na ladder. No? It's like ladder but not physical. Parang hierarchy, no? Parang hierarchy. More like, ano spell ng hierarchy? Ganyan ba? I don't know the spelling. Can you check the spelling for me? Hierarchy. Parang, o kaya, for example, yung mga ranking ng mga military. Or pag sinabi military echelon, ibig sabihin ito yung mga rank ng mga military of personnel natin. Okay? So, this matrix is in REF. Let's look at the second matrix. Is this in REF? Is there a 0 row? Yes, but it's in the bottom, so fine. Are the first non-zero entry from the left of the non-zero rows 1? Yes. Are they in echelon form? Yes. So, ito ay naka-R, EF. How about the third matrix? Is this in REF? What do you think? May 0 row ba? Yes. Yes, diba? Pero wala siya sa bottom kasi may non-zero sa ilalim niya, no? So, ito ay hindi REF. Lagay natin not in REF. So, siyang chance maging RREF kasi hindi na siya REF in the first place, right? Alright. Is this matrix in REF? May 0 ba? Yes. Tingnan natin yung mga first non-zero entry from the left. 1. Oops, there's a negative 1. So again, this is not. Isa lang ang ma-violate dun sa tatlo, hindi na REF ha. Last but not the least, may 0 row ba? Wala. So fine. First non-zero entry from the left, satisfied ba na puro 1? Yes. Satisfied yung condition number 2. Pero, are these pivots or pivots arranged in echelon form? No. Why? Kasi, kumanan ka pero bumalik ka bigla. Hindi yan echelon form. So, again, this one is not in REF. So, X na itong tatlo. Check natin ngayon, among the ones in REF, dalawa lang, no? Itong dalawa lang. Alin dito ang naka-RREF? Paano mo malalaman? You look at the pivots. Dapat, yung mga kasama ng pivot sa column niya, all are zeros. So, ito zeros to, zeros to, zeros to. Huwag mo nang titignan yung walang pivot. Just look at the columns with pivots. Dapat all other numbers in that column are zeros. Yes, looks like it is satisfied. So therefore, this is in RREF. Okay? Huwag nyo kakalimutan yung in kasi hindi tama yung grammar. Or is in. Is in. Ito. Nasa RREF ba to? Look at the pivots. Ito, pivots. Oops, yung second pivot natin, no? May katabing siraulo dun sa taas. So this is not in RREF. Okay? So, among the matrices, dalawa ang naka-REF. Dun sa dalawang naka-REF, isa lang ang naka-RREF. Do you understand? Do you understand? Okay, so what to do next? Our next lesson will be the question of, can we transform, let's say you have a matrix that is just not in REF. Can I transform it into something using a certain operation or algorithm? Can I transform it to a matrix in REF or better in RREF so that the corresponding linear systems that they represent are equivalent? Ba't gusto natin equivalent? Para pag na-solve mo yung isa, masasolve mo yung isa. Parang ang mangyayari ngayon, no, meron kang linear system, kukunin mo yung augmented matrix niya, yung augmented matrix niya, i-RREF mo, and then yung RREF, ang isa-solve mo instead. Kasi once na na-solve mo yung RREF na yon, na-solve mo na rin yung original na linear system. This is what we call as the Gauss-Jordan or the Gauss-Jordan algorithm. Gauss-Jordan method for solving linear system. Itong method na to ay hindi nagkakamali, no? Basta siya'y ginawa ng tama. And this is our topic for the next lesson. So, see you in the next one.